Hi guys, and welcome to this virtual lecture course in Classical Mechanics and Relativity. I'm Dr. Andrew Mitchell, and in this lecture I want to do something that many of you have been asking a lot about in recent times, to go through some specific worked examples. In the previous lectures we've been talking about the framework and the formalism of Lagrangian mechanics. We've really dived deep into the foundations of this theory, but we've not really applied it to any real-world examples. So in this lecture I really just want to go through several worked examples, line by line, all the gory details, so that you can tackle these problems yourself. In the first part of the lecture, we're going to talk about some very simple examples. We're going to talk about masses hanging off pulleys. We're going to talk about pulleys hanging off pulleys with masses hanging off them, simple pendulums, pendulums hanging off pendulums, all of this good stuff. These are really like classic classical mechanics problems. In the second part of the lecture, we'll talk about slightly more complicated problems. We'll talk about beads moving around on wires, which are themselves rotating. We'll talk about setting up the problem in generalized coordinates that are themselves rotating. We're going to see that the problems can be simplified massively by exploiting some of the conservation laws that we discussed in the last lecture. So the idea of this lecture is really just to go through several problems so you can see how it's done in practice and you can do it yourself. So that's what we're going to do in this lecture. Let's get down to work.
So having developed the Lagrangian formulation in the previous lectures, in this lecture I want to really just work through some examples to demonstrate how this is all working. I'll start off with some very simple and straightforward examples just to get the flavour for really how this works, and then I'll expand this to some more interesting and complicated examples in the later part of the lecture. So let's start off with possibly the simplest thing of two masses connected by a rope over a pulley. So this is a classic setup. We have a light frictionless pulley, and over it is draped a light inextensible rope, and at the end of the rope we have masses m1 and m2. This is the kind of classic setup for a Lagrangian mechanics question. You often see these kind of words appearing: light frictionless pulley, light inextensible rope, and so on, and it's worth just unpacking what those things mean. So when we talk about a pulley being light, it means that it doesn't have a moment of inertia. It doesn't have any dynamics of its own, so we don't consider, for example, the kinetic energy associated with the pulley. We also say it's frictionless, so the rope is not slipping over this pulley, dissipating energy. That's not what's happening. Also, the rope itself is light, so we don't consider the mass of the rope, and we consider it to be inextensible, so it's not sort of bouncy like a spring. So this is the simplest kind of thing we can imagine. When doing these questions, we should always draw a diagram to get our bearings, like the one that I've drawn here. We should also give a signing convention for how the coordinates are measured. So here I'll say that this is the x direction, and x is increasing as we go upwards. Let's also set the center of the pulley here as our x equals 0. So we can label on this diagram a distance from x equals 0 for mass number 1. Let's call that distance x1. And we can draw on the distance of mass number 2 from the origin as x2. So this is an effective one-dimensional system because the masses can just go up or down, and they're confined to the plane of the page here. So we have two masses, and therefore we need two coordinates to describe the position of these masses. These positions, x1 and x2, are coordinates measured with respect to our origin, x equals 0. So here you see that we have two coordinates, but we also have one holonomic constraint. A holonomic constraint, as you might recall, is a constraint equation that can be written involving only the generalized coordinates. And here we have a holonomic constraint because the position x1 is tied to the position of x2 through the length of the rope here. I didn't mention this earlier, should have done. this rope is of length L, the whole rope, that is. So what we have is two coordinates, x1 and x2, but also one constraint, and this means that in total we have 1 degree of freedom, and we can pick one generalized coordinate to describe that degree of freedom. So our generalized coordinate q is just going to be the x-coordinate, which is itself basically just x1. Let's say that our generalized coordinate is the position of mass number 1. Okay, so with all of that set up, and it's worthwhile really going through this to identify the coordinates, the degrees of freedom, the constraints, and so on. Once we've done all of that, we can finally write down the Lagrangian itself. We have a non-relativistic system here, so we just have the Lagrangian being the kinetic energy minus the potential energy. The kinetic energy is a half m1 times x1 dot squared for mass number 1, and a half m2 x2 dot squared for mass number 2. And the potential is going to be the potential due to gravity. For mass number 1, it's just m1 times g times x1. So it's just the mass times the gravitational constant g times the displacement x1. And what about for mass number 2? Very similarly, m2 g x2. So it's extremely simple when written in terms of the corresponding coordinates for the particles 1 and 2. What we now wish to do, however, is write this in terms of our generalized coordinate q, of which there is only one. And we can do that by employing this holonomic constraint condition. In particular, we can combine these expressions to say that x1 dot is equal to x dot, and x2 dot is equal to minus x dot. So here we're just taking the time derivative of this expression. In that case, the kinetic energy term just becomes a half m1 x dot squared plus a half m2 x dot squared minus m1gx plus m2g into L minus x, which we get just from substituting this expression in here. So that's the final result, and we can just sort of tidy it up a little bit to obtain the final expression, a half into m1 plus m2 x dot squared minus m1 minus m2 gx minus a constant m2gl. Now actually, it turns out that this constant is irrelevant to the following discussion, and that's because we're going to use this Lagrangian in the Euler-Lagrange equation of motion to actually find the dynamics of this system. And the Euler-Lagrange equation of motion is a differential equation. It involves on both sides of the equation derivatives of the Lagrangian. So any total constants like this can simply be ignored because they're going to drop out when we take the derivatives. So here is the Lagrangian written out again. I've dropped that constant now. And so the next step is to use the Euler-Lagrange equation of motion, which reads partial dl by dx is equal to d by dt of partial dl by dx dot for our single generalized coordinate x. This right-hand side here can be identified as simply the time derivative of the generalized momentum px dot. So what we have to do is simply calculate the derivatives of the Lagrangian with respect to x and x dot, and then plug it into this equation. So first of all, we have dl by dx, which is simply minus m1 minus m2 times g. We ignore all the terms involving x dot because we're talking about partial derivatives, and we're keeping x dot constant. However, when we calculate the partial derivative dl by dx dot, we treat x as a constant and only take the derivative of the x dot terms in the Lagrangian, which just gives us m1 plus m2 times x dot. We need to take the time derivative of this term. And so px dot, which is just the time derivative of this term, is clearly m1 plus m2 times x double dot, the second derivative of x with respect to time. So plugging into the Euler-Lagrange equation of motion, we have m1 plus m2 times x double dot is minus m1 minus m2 times g, or put another way, that's the acceleration x double dot is simply equal to m2 minus m1 over m2 plus m1 times g. The thing on the right-hand side is just a constant. It involves the masses, which aren't changing, and the gravitational constant here, g. And therefore, it's very easy for us to solve this equation. We can integrate it up, and we get the integral of x double dot dt is equal to the integral of this constant on the left-hand side. We're going to get simply x dot. On the right-hand side, we're going to get the constant times t plus a constant of integration, which I'll call c. But we're not done yet because we want to find the trajectory. We want to find x of t, and therefore we have to do yet another integration. So we just do exactly the same thing again. We integrate with respect to time once more, and this time we're going to get 1/2 times the constant times t squared plus c times t plus some other constant integration k. So because we had to do two integrals here to go from x double dot to x itself, we have two constants of integration. These can be determined from the initial conditions, or they could be determined, for example, from the positions of the particles at the beginning and at the end of some motion. In any event, we need two independent pieces of information to determine these two constants of integration, but once we've done that, we'll have determined the exact trajectory x of t. And finally, if we want to go back to x1 and x2, we can do that because we have an equation connecting the generalized coordinate x to x1 and x2. And this tells us what each of the two particles is doing as a function of time. Okay, so I went through that in quite a lot of detail, but I just wanted to make sure everyone's on the same page and we're able to do the basic examples before we move on to the more complicated things. So let's step up the complexity slightly now and consider another classic example. It's that of a double pulley. So this is the physical setup. We have two pulleys here. One of them is at a fixed position connected to the ceiling here. Over that pulley is draped a rope of length L1. That's this red rope here. At one end we have a mass M1, but at the other end suspends a second pulley. So this second pulley can actually itself move up and down. Over the second pulley is draped a second rope, that's the blue one, of length L2. And at the ends of that rope we have two more masses, M2 and M3. So let's define our coordinate system. We'll say that the x direction here is positive. And let's say that the centre of this upper pulley here, this first pulley, is located at the origin x equals 0. So here we actually have 4 moving objects. We have the 3 masses, m1, m2 and m3, and this second pulley here. This can also move up and down. And so to locate in the x direction each of these 4 moving objects, we need 4 coordinates. However, that's not the end of the story, because we also have 2 holonomic constraints in the system, namely the lengths of the rope. This rope is of a fixed length L1, and this blue rope here is of a fixed length L2. As we'll see, this corresponds to having 2 holonomic constraints, and therefore we have 4 coordinates minus 2 constraints gives us 2 degrees of freedom, and therefore we will be able to choose 2 generalized coordinates to describe the physics. Let's call those Q1 and Q2. To get us started, let's say that the x coordinate of mass number 1 relative to our chosen origin is precisely this degree of freedom Q1. In that case, we can then read off the position of the pulley as L1 minus Q1. And that's due to the holonomic constraint which connects the position of the pulley and the position of mass number 1 through the fixed length of the rope L1. Now, the beauty of generalized coordinates is that we can actually pick any coordinates we want to either make the calculation easier or perhaps to describe the physics that we're interested in describing in the most natural way. And in this case, a sensible and illuminating choice of coordinates might be to call this our second generalized coordinate Q2. It's the position of mass number 2 relative to the second pulley. So this is a nice choice of generalized coordinates because we'll be able to see how masses 2 and 3 bob up and down around their own pulley, which is itself something moving. So here we have generalized coordinates Q1 and Q2 labelled on the diagram. We have one other coordinate in here, which is going to be the position of mass number 3 relative to its pulley position, and that's going to be L2 minus Q2, and that is the second holonomic constraint. We're connecting mass number 3 and the position of mass number 2 to each other through the fixed rope length L2. So to summarise, we have 2 degrees of freedom in the system, 4 coordinates minus 2 constraints, and I'm making a choice for these generalised coordinates. I'm saying that Q1 is going to be the position of mass number 1 relative to its pulley, and Q2 is going to be the position of mass number 2 relative to its pulley, which is actually something that's moving. The pulley position here is actually completely determined through the rope constraint. It's completely tied to the generalised coordinate Q1, and the position of mass number 3 is completely tied to Q2 through the second rope constraint. So let's now specify the x-coordinates of these 4 moving parts in terms of our 2 generalised coordinates. Here are the x-coordinates of our 3 objects, the x-coordinate of the mass m1, the x-coordinate of the pulley, the x-coordinates of mass number 2, and the x-coordinate of mass number 3. The x-coordinate of mass number 1 is, by definition, simply the generalised coordinate Q1. The x-coordinate of the pulley is simply L1 minus Q1, whereas the x-coordinate of mass number 2 is the x-coordinate of the pulley plus Q2. To get the distance here, we need to add the distance of the pulley to Q2, but that can be written as L1 minus Q1 plus q2. And finally, the x-coordinate of mass 3 is this total distance, which is then clearly the x position of the pulley plus L2 minus Q2, which can be written simply as L1 plus L2 minus Q1 minus Q2. So these are the coordinates of our four moving objects. To work out the kinetic energy of the system, which I'm going to need for the Lagrangian, I'll actually also need to know the generalized velocities. So let's look at the corresponding velocities. Here I can write down the velocity x m1, which is clearly just the time derivative of our generalized coordinate q1 dot. I can write down the velocity of the pulley. So then I take the time derivative of the right-hand side here, but L1 is of course just a constant, and so this gives me minus q1 dot. I can look at the velocity of mass number 2, x m2 dot, and by similar logic, that's just minus q1 dot plus q2 dot, and finally x dot of m3 is minus q1 dot, minus q2 dot. Very good. So that's all we need to construct the Lagrangian, L, which is the kinetic energy minus the potential energy. Let's look at the kinetic energy first. It's a half mv squared for each of the three particles which have mass. Let me write that as the sum over particles I from 1 to 3 of a half mi into xi dot squared. And of course I can write that out in terms of our generalized coordinates explicitly. And now to get this expression, what about the potential energy? Here we have simply the potential energy due to gravity of the three particles. I can write that as minus the sum over I, again, from 1 to 3 for our three particles, of mi times g, the gravitational acceleration on the surface of the Earth, times the x-coordinate xi of the three particles. Again, I can write this in terms of the generalized coordinates very straightforwardly. I'll just tidy the algebra up a little bit and write this as the following. And here I actually threw away some of the irrelevant constants involving m, g, and the l's. I can throw those away because they don't affect the dynamics. The Euler-Lagrange equation of motion that determines the dynamics is a differential equation and therefore is blind to any constants we have in our Lagrangian. So here I've just thrown them away. The Lagrangian is therefore simply the kinetic energy that I've written here minus the potential energy. The next step is to plug this thing into the Euler-Lagrange equation of motion, which I've given here. We have one of these equations for each of the generalized coordinates. Here we have q1 and q2, so we have two equations. Notice in particular that this object on the right-hand side is actually simply pi dot. It's the time derivative, d by dt, of this object here, dl by dqi dot, which is the generalized momentum pi. So this object on the right-hand side is pi dot. So we have to calculate the derivatives of the Lagrangian that I just wrote down with respect to qi. and to qi dot in order to compute the equation of motion. So let's calculate the generalized momentum. Let's look at P1, which is dl by dq1 dot. On the last slide, I wrote out the Lagrangian, so here I can just take the derivative with respect to the generalized velocities, and I would obtain the following. And you should make sure that you can recover that same answer when you do it yourself. And likewise, for generalized momentum P2, which is partial dl by dq2 dot, I get this. That's very straightforward. And when I want to calculate the time derivative of this, which is on the right-hand side of the equation of motion here, I notice that the masses are all constants, and so P1 dot is just going to involve Q1 double dot and Q2 double dot. Okay, what about the left-hand side of the Euler-Lagrange equation of motion? This involves the partial derivatives of the Lagrangian with respect to the generalized coordinates themselves. And if I were to calculate dl by dq1, for example, this is very easy to see. That it's just this constant, whereas dl by dq2 is a different constant. And so here we actually have everything we need to write down the two equations of motions for our two generalized coordinates. I can now just equate the left and right hand sides. Equation of motion number 1 is simply dl by dq1 is equal to p1 dot, and that gives us this. Whereas equation of motion number 2, which is dl by dq2 is equal to p2 dot, gives us this. And these are the final results that we're looking for. We have two simultaneous equations here for the accelerations of the two generalized coordinates. In principle, I could solve these equations and eliminate, for example, q2 double dot and have an equation left over just for q1 double dot, and then I could very straightforwardly integrate that up to find the trajectory of q1. Having done that then for q2, I can then find the trajectories of all the original moving particles in the system, x1, x2, x3, and the x-coordinate of the pulley as well. The setup that I've given here is actually quite a nice way of setting up the problem in terms of these generalized coordinates, because it's quite obvious from looking at these expressions that we have an equilibrium condition when m1 is equal to m2 plus m3 and m2 is equal to m3. And that's because from this first condition, the right-hand side here is equal to 0, and from the second condition, the right-hand side here is equal to 0. And that means all of these accelerations are going to have to be equal to 0, and therefore we have an equilibrium situation. And that makes physically good sense. If I remind myself of the physical setup, which I've drawn again here, you see that if m2 and m3 collectively add up to m1, then that means that this pulley is balanced. Likewise, if m2 is equal to m3 as well, then this pulley is balanced. So you see that equilibrium condition very naturally in these equations that I've written down here. So the next example is a very simple example. It's that of the planar pendulum. We've actually looked at this one previously, but let's just do it again, this time in full detail. So here we have a single particle that is confined to the plane of the page here. That's what I mean when I say it's a planar pendulum. So all it can do is swing backwards and forwards, and it's pretty clear, therefore, that there's just one degree of freedom here. But let's again just rehearse the argument for why we have that. First of all, we have one particle in 3 dimensions. That means we have an x, y, and a z coordinate, but we have 2 constraints. And these are holonomic constraints because I can write them as an equation involving the generalized coordinates. First of all, I said this is a planar pendulum, and so I can confine the particle to the xy plane and set z equals 0. That's an equation rather than inequality, and it doesn't involve generalized velocities, only generalized coordinates. There's also the pendulum constraint, which is that x squared plus y squared is equal to L squared. There's a fixed distance of the mass here from the pivot point. So we have two equations involving generalized coordinates, therefore we have two holonomic constraints. They reduce the number of degrees of freedom from 3 to 1. So we have 1 degree of freedom. I'm going to let the generalized coordinate q be the angle theta, and the angle theta I'm going to draw on the diagram here is the angle from the vertical. Let's say that the bottom of the swing of the pendulum here, we'll say this is the origin of our coordinate system x equals 0, y equals 0. So now we can just go right ahead and write down the Lagrangian. It's the kinetic energy minus the potential energy for the single particle. The kinetic energy can be written in its component form in terms of x dot squared plus y dot squared, which in turn can be written in terms of the angle theta, which is our generalized coordinate. So how do we do that? Well, first of all, let's say that we have a position vector r in terms of Cartesian coordinates x and y. This is equal to L into sine theta 1 minus cos theta relative to our origin of our coordinate system, which is this point at the bottom of the swing here. I can now take the time derivative of this to find the vector r dot. L is a constant, and so this is just going to give theta dot cos theta and theta dot sine theta for our velocity vector. And in here we have the velocity vector squared, r vector dot dotted into r vector dot. So that's just a shorthand notation for this dot product, which is clearly L squared theta dot squared, using the identity that cos squared plus sine squared is equal to 1. So actually, it's very straightforward to write our Lagrangian in terms of theta. And then we subtract off this constant mgl here. As usual, the constant doesn't matter in the Lagrangian, so I'm just going to ignore that in what follows. Now we want to proceed with the Euler-Lagrange equation of motion, which in the theta coordinate is p theta dot is equal to partial dl by d theta. So first of all, let's work out p theta, which is partial dl by d theta dot. That's not so difficult. It's just ml squared theta dot. Therefore, p theta dot is ml squared theta double dot. On the right-hand side of the equation of motion here, I have dl by d theta. That's also very simple. It's just minus mgl sine theta. So I have everything that I need to write down the equation of motion. And I get that theta double dot plus g upon l sine theta is equal to 0. That is a simple differential equation. For small theta, we can make the approximation that sine theta is approximately theta, and then we would have regular simple harmonic motion as the solution to this equation. Without further ado, let's now consider the spherical pendulum, or three-dimensional pendulum. In this problem, we have again a single mass at the end of a pendulum of length L. However, the pendulum is free to move out of the plane of the page as well. So not only does it bob backwards and forwards, but it can sort of spiral around, as I've indicated here. So this spherical pendulum is actually identical in its physics to a particle rolling around in the inside of a hemispherical bowl. Imagine that I have a bowl, as depicted here, and I put a particle in it, and the particle is confined on the inside of the bowl, so it's rolling around on the inside of the bowl, and it can sort of make patterns like this as it spirals around on the inside of the bowl. So this is actually the same problem as the spherical pendulum, because both of the systems essentially have a pendulum constraint. Here we see that the length of this line L here is fixed. It's the distance of the particle from this origin, and that's basically the same constraint as saying the bowl is of a fixed radius and the particle is confined to move around on the inside of the bowl. So actually both of those problems are equivalent. So here we have 2 degrees of freedom, which we can describe by 2 angles. Let's do it in spherical polar coordinates, and let those angles be theta and phi, the polar and the azimuthal angles, respectively. So the reason why we have 2 degrees of freedom here is because we have a particle in 3 dimensions with 1 holonomic constraint, the pendulum constraint. So 3 minus 1 is 2, and we're describing those 2 degrees of freedom with 2 generalized coordinates. So naturally, because this problem has a spherical symmetry, we'll be using the spherical polar coordinates. So first of all, let's define our position vector r of the particle. It's going to be a length L away from the pivot, and in spherical polar coordinates, this is a result you can simply look up. I can write down the r coordinate as follows. What I will need to know for this is both the position and the velocity. Let's work out, therefore, the corresponding velocity. We have to take time derivatives of those things, noticing that theta and phi both implicitly depend on time. And we have to use product rule, therefore, and we get a bunch of terms, which are the ones that I've written down here. What we want to know in order to work out the kinetic energy is phi vector dot squared, which is phi vector dot taken with the dot product with itself. And I'll leave it as an exercise for you to multiply all of that out, but it's not so hard. What one gets is L squared into theta dot squared plus sine squared theta phi dot squared. And again, here I'm utilizing the trigonometric identity that cos squared plus sine squared is equal to 1. Okay, so back to the Lagrangian. It's T minus phi. The T is the kinetic energy, a half m r vector dot squared. We've just worked that out, or the difficult part of it anyway. And the potential is simply mgl cos theta. So overall, we have a very simple Lagrangian. One thing we can already see from this Lagrangian is that the coordinates, the generalized coordinate phi, does not appear in this Lagrangian. Phi dot appears, and theta appears, but phi itself does not appear. That means that phi is a so-called cyclic coordinate. Lagrangian doesn't depend on phi, and therefore the corresponding generalized momentum, p phi, is conserved. This is a consequence of Noether's theorem, which we considered in the previous lecture. So maybe already at this stage we should actually work out what p phi is. We know that it's dl by d phi dot by definition, and that's easy to work out from the expression. It's ml squared sine squared theta phi dot, which is, of course, exactly the angular momentum around the z-axis. And of course, this is exactly what it should be. We have a pendulum here which is swinging around, and whatever angular momentum it initially has is a constant and remains conserved throughout the motion. So there's an angular momentum which is conserved in this direction here around the z-axis. The angular momentum around the x and y axes is not conserved because, of course, the particle is subject to gravity, and therefore the potential changes as we go up and down. We don't have a rotational symmetry in the other directions. We only have the rotational symmetry around the vertical axis. So there's no equation of motion we need to do in the phi coordinate because we know that this quantity involving p phi is simply a constant. But what about in the theta coordinate? Here we can actually calculate Euler-Lagrange equation of motion. So let's go ahead and do that. We're going to look at the Euler-Lagrange equation of motion in the theta coordinate. Let's look at p theta first of all. That's dl by d theta dot, which is simply ml squared theta dot. I can calculate, therefore, p theta dot, the time derivative of that, ml squared theta double dot. And from the Euler-Lagrange equation of motion, we know that that quantity should be equal to partial dl by d theta from the Euler-Lagrange equation of motion. And this quantity, when you work it out, is simply ml squared sine theta cos theta phi dot squared plus mgl sine theta. So to summarize, the equation of motion along the theta direction is as follows. And this is the result once we've cancelled a few irrelevant factors. And furthermore, we can actually make an additional simplification because this is a differential equation that involves both theta and phi dot in here, but phi dot is actually related to the angular momentum Lz, which is constant and conserved. So what we can do is actually rearrange this expression for phi dot and substitute it in here. That will eliminate all of the phi dependence from this equation, leaving only things involving theta, m, l, and Lz, which is a constant. That means this equation then becomes easy to solve. Or I should say, easier to solve. So this is an example of how identifying conserved quantities really helps us in finding the solutions to the problems, not only in revealing conservation laws and something interesting about the physical problem, but actually helping us with the mathematics of the solution itself. Let's consider another example now, also with a rotational symmetry, which is a particle in a cone. The physical setup is that I have some kind of cone, as you see here, and a single particle which is rolling around on the inside of the cone, so I don't allow it to leave the surface of the cone. I've drawn on my axes here, my right-handed set of Cartesian x, y, and z axes. The cone itself has to be parameterized by some angle, and I'll choose this opening angle here of the cone from the vertical z-axis to be some angle alpha. So an appropriate coordinate system for this problem would be cylindrical coordinates, and that's because we have a rotational symmetry in the xy plane, but the z-axis is different. So I will choose a position vector r, which in our original Cartesian coordinates x, y, and z are going to be related to our cylindrical coordinates r cos theta, r sine theta, and z. So we have one particle in 3 dimensions, which requires 3 coordinates to specify its position. However, we have one holonomic constraint. And that is the fact that the particle is confined to the surface of the cone. How do we define that? Well, basically, we can specify that the radius is always related to the height, z, through the angle phi. And if you do a little bit of trigonometry, you realize that r and z are not independent. They're related to each other. As I go up the cone, the r coordinate has to also increase. So, this is a constraint equation. It involves the generalized coordinates rather than generalized velocities. It's an equation, so it's a holonomic constraint. That means it reduces the number of degrees of freedom, and therefore I have 2 degrees of freedom, and I'm going to choose those degrees of freedom to be r and theta. I can eliminate the coordinate z from the equations using this holonomic constraint equation. So this choice of coordinates, generalized coordinates, is a good choice. They are complete in the sense that all points on the cone are describable by only r and theta once we know the angle alpha of the cone. These 2 generalized coordinates are also independent, meaning that we have a full range of movement for r when we fix theta and vice versa. Okay, so we're now in a position to write down the Lagrangian, or almost. We should work out the velocity vector first, which is d by dt of the r vector. Let me just write it down. We just have to remember to use product rule because both r and theta have a time dependence. And on the last line here, I've actually replaced z by r upon tan alpha. 1 upon tan alpha is cot alpha, and so that's this term here. Let me also change the z in our original expression here for r cot alpha. Notice that alpha is a constant, it doesn't change with time. We can now write down the Lagrangian The kinetic energy is something that only depends on the velocity squared, while the potential is something that only depends on the vertical displacement z, which we've now reparameterized in terms of r cot alpha. So we can go ahead and use these expressions to write down the Lagrangian. With a little bit of algebraic manipulation and simplification, it's fairly straightforward to show the following. Have a go at it yourself if you're not sure. Notice in this expression that r and theta are the generalized coordinates. We have a parameter alpha here that is just simply a constant. Notice that in our Lagrangian, that theta is a cyclic coordinate. Theta does not appear in this expression. Theta dot appears, but not theta itself. And again, that's to be expected because we have a continuous rotational symmetry in this problem in the xy plane, and that will correspond to a conserved angular momentum around the z-axis, as we've seen many times in the previous lectures and even in this lecture. So theta is cyclic. That means that dl by d theta is equal to 0, which means, in turn, that p theta is a constant. We just use the Euler-Lagrange equation of motion to discover that p theta dot is equal to 0. So p theta itself is a constant. What is p theta? Well, of course, it's dl by d theta dot, and in this case, we can just write that down. It's mr squared theta dot. So this is quite interesting, because both r and theta are dynamical and change with time, but the combination mr squared theta dot is constant throughout the motion. And furthermore, we know that this object is actually the angular momentum around the z-axis. So let's now proceed to work out the Euler-Lagrange equation of motion for the r coordinate. This is going to be dl by dr is equal to d by dt of dl by dr dot, and that latter object is the generalized momentum conjugate to the coordinate r, pr dot. I leave that for you to do yourself. Let me just finally write down the answer, which is that r double dot into 1 plus cot squared alpha is equal to r theta dot squared minus g cot alpha. Again, this equation might look quite difficult because it's a differential equation for r double dot involving r here, but also theta dot. However, we can exploit the fact that p theta is a constant to get rid of this theta dot in here. We can relate theta dot to a constant and r. And that means that we can recast this entire differential equation here just in terms of r double dot and r. We can totally eliminate the theta dot dependence through this nice expression. We're basically exploiting the conservation law in the problem that angular momentum is conserved. The next example is something a bit more interesting. It's a bead on a wire that is itself rotating. So let's imagine that we have a wire of some particular shape, that's this black thing, and we have a particle which can slide freely along the wire. So this red particle here can slide up and down and around on this wire. And the whole thing is subject to gravity, which is a force acting downwards in this case. So let's draw on our coordinate system. Let's just choose Cartesian coordinates for now. So let's say that we have the xy plane being the horizontal plane here, and z is the vertical axis. I'm centering the origin of this coordinate system down here at the bottom of our wire. Now let's imagine that we start our wire spinning around this axis, which is the z-axis, and it has an angular velocity of omega. So intuitively we can guess what will happen. As we start the wire spinning, there will be a centripetal force which will fling the particle outwards, and therefore it will climb up this wire. That's what we can guess. So let's solve this problem properly using Lagrangian mechanics and see exactly what happens. One interesting thing we'll be able to calculate is which angular velocity omega is required for a given shape of wire to have a particle in equilibrium suspended at a particular point in the wire. So we'll see when that condition arises. So first of all, let's be a little more concrete. Let's say that the wire itself has a parabolic shape. So this is roughly as I've drawn it. And by parabolic shape, what I mean is that the z-coordinate is connected to the radius by this equation with some constant c. By radius here, I'm referring to, let's say, the particle as at a distance z on this axis, and the radius is exactly this distance from the z-axis. I'm calling this distance from the z-axis here r rather than y because, of course, the wire will be rotating and can move out of the yz plane. But the distance from the axis is always a constant r for a given height z. And z and r are connected by this parabola equation here. Let's also say that the wire is rotating with a constant angular velocity. So in particular, the angle theta through which the wire has moved will simply be related to the time through omega t. So what is this angle theta, to be more concrete? Well, let's say that we drop a perpendicular from our particle, and let's say that it's making some particular projection here onto the xy plane. Let's measure this angle theta as the angle of this wire from the x-axis, as shown. So here I probably should have drawn these green things in a bit of perspective. Let me just do that so the diagram is completely clear. This should really be at an angle like this. That is the distance r from the z-axis, and this is the total height z. Okay, good. So here I've drawn in the Cartesian coordinates. However, because there is a rotational symmetry of this problem, the wire is spinning around the z-axis, it makes sense to use cylindrical coordinates. So they are going to be the coordinate system we'll use. So what we can do is say that our generalized coordinates q are r, theta, and z. However, we have two holonomic constraints in here. First of all, we know that the angle theta is completely determined, so this is not a variable. At a given time t, we know exactly what's happening to theta because omega is a constant. Also, in this expression, we have r and z, but r and z are connected through this constraint equation here. So really, we only have 1 degree of freedom. And of course, that's kind of obvious from the diagram. This particle can only go up or down along this wire. There's just 1 degree of freedom as it slides at some point along this wire. The fact that the wire is spinning doesn't matter. That's not actually a dynamical variable. It doesn't correspond to a degree of freedom. So we actually only have 1 degree of freedom in this system, and therefore I will actually cross that out. We don't want to describe our generalized coordinates as r, theta, and z, but simply a single degree of freedom, q, is equivalent, let's say, to r. I could have picked any of them, but I chose to pick r. Okay, so let's now write down the Lagrangian. It's T minus V. Let's look at the kinetic energy term first. In one of the previous examples, we worked through explicitly what the kinetic energy looks like in cylindrical coordinates, so I won't repeat that. The nice thing about this process is when you've done it once, you've done it, and you don't have to do it again. So I'll just repeat the answer that we had from previously. And we have this, but actually we can simplify this quite a bit, because theta dot in here is actually the angular velocity. It's obviously the angular velocity, but also we can see it directly from this equation. If I were to take the time derivative of this, then we'd see that theta dot was just omega, which is itself here a constant. Also, z is actually connected to our coordinate r, so I can take the time derivative of this and substitute it in here. And when I do that, I will get a kinetic energy that looks like the following, just in terms of our coordinate r and the constant angular velocity omega. So we get something like that. What about the potential? The potential is just that due to gravity, which depends on the vertical displacement. That's mgz. We can again convert that into our r coordinate, mg constant c times r squared. Good. The full Lagrangian is just the difference of those two terms, and therefore we can apply the Euler-Lagrange equation of motion in our single generalized coordinate r to find out what's going on. This means dl by dr is equal to d by dt of partial dl by dr dot, that latter thing being pr dot. So let's just work those terms out term by term. dl by dr dot is mr dot plus 4 c squared r squared r dot. And if we take the time derivative of that, that thing is called pr dot. And that thing is obviously mr double dot. Then we've just got to be careful to use product rule on these multiple terms, each of which depend on time. And we get this expression. So this is just straightforward differentiation. We're not quite there yet because we need to work out this first term, partial dl by dr. That's not so difficult, but we still need to go ahead and do it. That gives us m lots of 4 c squared r dot squared plus r omega squared minus 2g cr. So we actually have everything we need here in our equation of motion. So let's just tidy this up and cancel a few terms and see what we get. So this is the final expression, our equation of motion, and it actually looks like rather a complicated expression. We have the acceleration along the r coordinate here, but this equation of motion also involves the r coordinate and also the velocity along the r direction. So this is not a completely straightforward equation to solve, but it is in principle solvable analytically, as well as using a numerical simulation of the dynamics here. But let's actually use this equation to figure out something rather simple. Let's work out what happens at equilibrium. At equilibrium, we see that the acceleration should be 0 and the velocity should be 0. The particle is just at some particular point, it's in steady state, and it's on the wire at some particular r. It's not accelerating and there's no velocity. So let's go to our equation of motion here and see what this equilibrium condition implies. We can simply set r double dot to 0 and r dot to 0, and then we're left with this term being equal to 0. And we see something rather interesting. We have r, which is at the equilibrium point, into 2gc minus omega squared is equal to 0. And this equation can be satisfied in two ways. We see that we can satisfy this equilibrium condition either by the equilibrium radius being equal to 0, and what that means is that here the particle is actually sitting right at the bottom. That's actually an unstable equilibrium position. If you imagine this wire spinning around very, very quickly, if the particle is sitting right at the bottom, then there will be no forces acting. But if I nudge it ever so slightly away from its equilibrium position, it will get flung off and zoom up the wire. So this is an equilibrium condition, but it is an unstable equilibrium. And you can't see that just from this condition, but you can reason it from here, or equivalently, you could analyse the problem further by looking at the susceptibility of the motion to an infinitesimal perturbation. What about the second condition here? This is actually non-trivial and something you might not have guessed. What it tells you is that if the constant angular velocity omega takes a very special value, namely the square root of 2gc, where g is the gravitational acceleration, and c here is this constant parameterizing the shape of the parabolic wire, then we have an equilibrium condition. So if I get the angular velocity just right, then it means that the centripetal force will exactly balance the gravitational force, and that means that the particle will remain in equilibrium, and this actually doesn't depend on the radius. So I can actually put the particle anywhere I like on this wire, and it will stay there in equilibrium, providing that I get this angular velocity condition correct. So that's a non-trivial result that we've learnt from the full solution of this problem. Let's have a look now at a different but related problem of a particle moving around on a circular wire which is spinning around its z-axis. So it has some similarities to the problem we've just studied, but there are also some differences. In the end, I will solve the underlying equations of motion of this system numerically rather than analytically using the package Mathematica. So let's have a look at that now. So here is the animation. I have a ring and a particle on that ring, and if I don't have the ring spinning, the particle will just move backwards and forwards. It's basically simple harmonic motion. It's pendulum behaviour. More interesting behaviour happens when I start to spin the ring let's say a fairly slow velocity, and we see that basically we still have the same kind of motion. The particle swings backwards and forwards, and as I increase the speed, at least as long as the angular velocity is not too great, we have basically the same kind of physical picture. However, you might see some slightly different behaviour here, and that's because as we increase the angular velocity of the ring, the ball is being sort of flung outwards a little bit more. And we see this very starkly if we have a very, very large angular velocity of the ring, in which case the ball is flung outwards to its most extreme point, which is basically its start position. So if I start the animation going now, you'll see the ball basically does not fall under gravity. Actually, there is a small perturbation here, it's just you can't really see it. If I were to decrease the speed here, you see it starting to sort of bob around a little bit, around that main position. And as I make it go a bit slower, you see it starts to fall a bit lower due to gravity. But basically, it's executing some kind of simple harmonic motion, but the axis, instead of being vertically downwards, is then shifted due to this additional centrifugal force. In the next example, I want to consider a ball being thrown inside an elevator. This might seem a little bit esoteric, but actually there are some interesting things that come out from this thought experiment. And indeed, it's exactly these kinds of examples that Einstein considered when inventing the general theory of relativity. We'll see something here akin to Einstein's equivalence principle. We will see that acceleration due to the moving elevator and gravitational force are essentially interchangeable. Okay, so let's describe the setup. So here we have an elevator, and it is moving upwards. Let's say the ground is over here, and the height of the floor of the elevator above the ground is something that I will call h of t. It's something that changes with time. So let's be a little bit specific. Let's say that at time t equals 0, h of 0 is equal to 0. So we're saying that at time t equals 0, the elevator is resting on the ground. Let's also suppose that the elevator is accelerating upwards with a constant acceleration a. So I can express this as h double dot of t is actually equal to a constant a. And that is something that does not change with time. It's a constant. Furthermore, let's say that at t equals 0, the elevator has some particular velocity v0. That means that h dot of t equals 0 is some constant v0. This all allows me very straightforwardly to describe the full trajectory of the floor of the elevator. I can say at the floor of the elevator, h of t is going to be v0 t plus a half a t squared. I get that simply by integrating this expression for h double dot twice and using these boundary conditions that h0 equals 0 and h dot 0 equals v0 to fix the two constants of integration. Then I find this expression for the height of the floor of the lift above the ground as a function of time. Okay, so all of this is not particularly interesting so far, so let's spice it up a bit. Let's say that we have a ball inside the elevator which is thrown up with a velocity of u0 relative to the floor of the elevator. So let's say that I'm standing in the elevator, and in my reference frame, I simply throw up the ball with a velocity u0, but that u0 is a velocity that's relative to the elevator itself, not to the ground. So of course it's crucial here that the velocity u0 be relative to the elevator. So let's imagine now the ball at some generic point in its trajectory. So I will erase this picture of the ball and now draw in the ball at some later time where it's up in the air somewhere. Let's introduce two quantities. I'm going to introduce here the height of the ball above the floor of the elevator. That quantity, for the sake of argument, I will call q of t. I will also define the height of the ball above the actual ground, and let me just call that z of t. This is actually the trajectory that we want in the end. It's the position of the ball relative to the ground. That's a trajectory, z of t, that depends on time. So clearly from the diagram we have that z of t is equal to q of t plus h of t. The height of the ball above the ground is equal to the height of the ball above the floor of the elevator plus the height of the elevator above the ground. And here we already wrote down h of t explicitly because we knew that the elevator is accelerating with a constant acceleration a with initial velocity v0. Okay, so the challenge now is to really work out the trajectory of the ball. How do we do that? Well, of course, we use Lagrangian mechanics. We'll write down the Lagrangian of the system, and by the system here, I mean let's focus on the dynamics of the ball itself. As usual, the Lagrangian is t minus v. That means a half times the mass of the ball times z dot squared. This is the velocity of the ball relative to the ground, minus the potential energy, which is simply mg, and then the vertical displacement above the ground, which is mgz. This is the Lagrangian in a generalized coordinate z, describing the displacement of the ball above the ground. However, I can actually also convert this to a different generalized coordinate, namely the q coordinate. I can describe the Lagrangian in terms of the position of the ball relative to the elevator itself. Luckily, I have an expression that connects z to q through this function h, which is actually known. So it's very simple, therefore, to write down our expression for the Lagrangian in terms of our generalized coordinate q instead of z. It takes a little bit more of a complicated form, but you can convince yourself pretty easily that this is the result. Here I had to substitute in the expression for z, and here I had to substitute in the expression for z dot squared, and z dot is obtained simply by taking the time derivative of this expression. So here let me re-emphasize, in the first expression I have written a Lagrangian in terms of generalized coordinate z, and in the second expression, which is completely equivalent, I've written it in terms of the generalized coordinate q. Those quantities are defined by this diagram up here. Okay, so let's now actually work out the dynamics of the ball using our familiar Euler-Lagrange equation of motion. And I'm going to actually do this in both of our coordinates, the z-coordinate and the q-coordinate, and then compare the two at the end and try to understand physically what this is telling us. And we'll see that there are actually some interesting things coming out of that. First of all, let's do it in terms of the generalized coordinate q. The Euler-Lagrange equation of motion reads partial dl by dq is equal to the time derivative d by dt of partial dl by dq dot. We have the explicit expression for the Lagrangian in terms of the q coordinate here, which, just to remind you, is the relative position of the ball from the floor of the elevator. And I can just go ahead and calculate all of these necessary terms. In particular, the one on the left-hand side, dl by dq, is particularly simple. It just gives minus mg. dl by dq dot, likewise, is fairly straightforward. It's m into q dot plus v naught plus a times t, and we need to take the time derivative of that, which in the end is going to give us simply mq double dot plus ma. The constant mv here simply drops out when I take the time derivative. Okay, very good. Now I can equate the left-hand side and the right-hand side of the equation, cancel the factors of m all round, and I find simply that the acceleration q double dot is equal to minus g plus a. I can now integrate this up twice to find the trajectory q of t, which is what we really want to know here. I will have two constants of integration, but I also have two boundary conditions. I know that at t equals 0, the ball is resting on the floor of the elevator, which means q is equal to 0. I also know that at t equals 0, the ball was thrown up with a velocity u0. So I can use those two things to determine exactly the trajectory q of t. I'll leave that for you to do. It's very simple, and this is the final result. Now, this trajectory equation is actually extremely interesting. Why? Because it's exactly the expression one would normally expect for a ball being thrown on the surface of the Earth. You throw a ball up with a velocity u0, and it has exactly this expression where we have an acceleration due to gravity, except, in this case, the gravitational acceleration g is actually replaced by g plus a. From this trajectory, it looks like gravity has just got stronger. It looks like instead of g, we have g plus a. The acceleration of the elevator here enters into the trajectory in exactly the same way as the gravitational acceleration. Another way of saying this is that we can kind of regard the gravitational force as actually just an acceleration. In terms of trajectories in classical physics, we would not be able to distinguish between some trajectory that was caused by an accelerating reference frame as opposed to a trajectory that was caused by some gravitational force. And this is basically Einstein's equivalence principle. You can think about gravity as an acceleration. Of course, that's simplifying it a little bit, but it's the basic idea. Okay, so that was rather interesting. Let's now have a look at the equation of motion written not in terms of the q-coordinate, but in terms of the z coordinate. We now have instead dl by dz is equal to d by dt of dl by dz dot. I can either go back to my original Lagrangian here and just compute this, or I can go to my expression for q of t and simply relate it to z of t through the h of t expression that I had on the previous slide. When I do that, of course, I get the same result in both cases, and I find a trajectory when I solve that expression z of t, which is equal to u0 plus v0 of t minus a half gt squared. So this is the trajectory of the ball in the reference frame of the ground, not in the reference frame of the accelerating elevator, but relative to the static ground. And we see this is a different reference frame, a different point of view, and we get a different interpretation of the physics. Z of t here looks like the same equation we would normally expect for a ball thrown under gravity. The strength of the gravity here is exactly what we'd expect it to be, g, because we're standing on the ground and we're subject to a regular velocity. But this time, the initial velocity is supplemented by the initial velocity of the elevator. So from the perspective of the ground, when we throw the ball inside the elevator, we have to add the velocity with respect to the elevator and the velocity of the elevator itself. So that's u0 plus v0. So these are two different ways of viewing the same physics. From the perspective of the ground, we throw up the ball and it just has a higher initial velocity, but it still accelerates under gravity. Whereas relative to the elevator, the initial velocity is just the velocity relative to the elevator, but it feels like gravity itself is stronger. I should emphasize the physics here is really the same, it's just a matter of our reference frame. Of course, we'll be coming back to the study of reference frames in special relativity and an outlook towards general relativity later on in this course. But here I just wanted to introduce you to a few of these rather interesting concepts that arise already in the simplest possible classical mechanics problems. In the next example, I want to consider something that actually has a somewhat similar flavour to it. This is a bead, a particle, moving around on a wire which is shaped into the form of a circle, a ring. However, this ring is itself in motion. In this example, we're going to actually transform to a set of generalized coordinates that are co-moving with the ring. Okay, so let's see what the setup is in detail. So imagine here that I have a wire ring of radius, let's call it b. And so let me draw on here a diameter, and the radius here is b, that's b, and this on this side is also b, passing through the centre here, which I've marked with the x. And the idea is that this ring is actually going to be rotating around a point on its circumference. So you imagine this point here that I've denoted with this red dot here. Let's call that point P. So let that point P be the origin of our Cartesian coordinate system. So this is going to be the x-axis, and then we have a vertical y-axis, and everything that I'm going to describe here will be in this xy plane. So nothing's happening in the z direction, there's no effects of gravity here, everything is just happening in the horizontal xy plane. So there's no gravity in this problem. So this point P, which is on the circumference of this ring, is something that is fixed, and this ring is itself something that is moving around this fixed point P. So we imagine the ring itself is rotating. How can I describe that? Well, imagine that I draw this diameter, as I have done, from the point P, passing through the centre, this defines an angle to the x-axis, which I will call phi. Let's say that the ring is rotating in the xy plane with a constant angular velocity. Phi is equal to omega t. Omega here is a constant angular velocity. Okay, let's make it even more interesting. Let's put our particle, our bead, somewhere on this wire. This particle can freely move without friction backwards and forwards anywhere around this wire. It can pass through the point P if it likes and go back again. So this particle is free to move around the wire, but the wire itself is also executing this circular motion with a constant angular velocity omega around the axis, which is something passing through the point P on the circumference. Everything is happening in the xy plane. What we want to do is describe the dynamics of the particle moving around on this ring. So how should we do that? First of all, we need to identify a generalized coordinate. Now, we've done this enough times now to realize that if we have a particle moving around on a wire, then it has 1 degree of freedom. It can either move forwards or backwards. It's just confined to this ring. Therefore, let's define an angle of the particle relative to the center here, and the angle is going to be the angle here, which I'll mark as theta. It's the angle between the line from the particle to the center and the diameter, which is the center of the ring, to the point P. Now, the reason why it's a good idea to choose our generalized coordinate as theta here is because this angle theta is itself relative to the diameter, the blue diameter here, which is something that is itself rotating. So by choosing theta as our generalized coordinate, we're actually going to the co-moving frame of this ring, which is rotating. It's a very simple way of adopting the rotating reference frame. So the generalized coordinate that we'll choose here will be simply the angle theta as indicated on the diagram. To be able to write down the Lagrangian and to solve for the dynamics of theta, we're going to actually need to write down the x and y coordinates of our bead in terms of theta. How do we do that? Well, let's break up the x coordinate into 2 pieces. We have this length here. By trigonometry, that is clearly b cos phi. Then we have this additional projection onto the x-axis. How do we work that out? Well, first of all, note that the red line here is also a radius and therefore also has a length b. But the angle relative to the x-axis is now this combined angle theta plus phi. And so this extra piece here is actually b cos of theta plus phi, which we can read off from the diagram. So our x-coordinate is actually b cos phi, phi is omega t, plus b cos theta plus phi, which is theta plus omega t. We can do exactly the same for the y-coordinate. Actually, we just have to replace the causes by sines. And therefore, we've obtained the expression for the position of our bead in terms of the angle theta. For the Lagrangian, we're also going to need to know the velocities. So let me work out x dot and y dot. We just have to take the time derivative of these expressions. Note that omega is a constant. We're going to find minus b omega sine of omega t minus b and then theta dot, because theta is a dynamical variable that has a time dependence, plus omega, into sine theta plus omega t, and then the corresponding expression for the y-coordinate. Our Lagrangian, therefore, L is T minus V, is actually just the kinetic energy T, because as I mentioned, everything is happening in the xy plane. There's no effects of gravity here. So the kinetic energy is just a half m times the velocity squared. In component form, that's x dot squared plus y dot squared. And I've just worked out x dot and y dot, so I can substitute that in. What I will find is that I get a bunch of cos squareds plus sine squareds, and as a trigonometric identity, we know that cos squared plus sine squared is equal to 1 for any angle. And so let me just write down the simplified result. You can check this yourself. Making that simplification, we obtain the following form for the kinetic energy. And the kinetic energy is itself, in turn, basically the entire Lagrangian. So we get this somewhat complicated expression here for our Lagrangian in terms of our generalized coordinate theta. So let's proceed to use the Euler-Lagrange equation of motion to actually find the dynamics of this system. We have a single generalized coordinate. Let's go through the motions. The equation of motion is dl by d theta is equal to d by dt of dl by d theta dot. The generalized momentum is partial dl by d theta dot, so let's just work that one out first. From this expression, it's straightforward to see that this is just going to be mb squared into theta dot plus omega cos theta. Of course, what we actually need here on the right-hand side is the time derivative of that. So p theta dot is what is really on the right-hand side here. And I just have to take the time derivative of that, noting that theta dot and theta both have a time dependence. And then I obtain mb squared into theta double dot now, minus omega theta dot sine theta. Whereas dl by d theta on the left-hand side is going to be simply minus mb squared omega into theta dot plus omega sine theta. So putting all of that together, let me summarize. We have an equation of motion which is minus mb squared omega theta dot sine theta on the left-hand side minus mb squared omega squared sine theta, just expanding out this bracket here. And then on the right-hand side, we have mb squared theta double dot minus mb squared omega theta dot sine theta. Now, something extremely interesting happens. This complicated expression actually simplifies because the same term arises on the left-hand side and the right-hand side of the expression. This term cancels with this term. This is not, of course, by accident. So to explore that, let me just cancel a few things and tidy up the expression. So the equation of motion will take the final form as follows. This is rather interesting because we've seen this expression before. It's the equation of motion for a simple pendulum. And in particular, we can actually make this analogy concrete. and say that this system in the dynamical generalized coordinate theta behaves exactly like a simple pendulum of length L, which is g over omega squared. G, of course, the acceleration due to gravity, and omega here being the angular velocity of this ring. So why on earth is the equation of motion for a simple pendulum hiding inside this very, very complicated system when we go to the rotating frame of reference? Well, actually, physically, it makes quite a lot of sense. We have here a system which involves this ring, which is rotating around this point P, and that will provide a centrifugal force that's flinging the particle outwards away from the point P. In the rotating frame of reference, the co-moving frame of reference with the ring, this force is always acting outwards along this blue line here. This is the centrifugal force that's pushing the particle outwards. In the co-moving frame, it's always moving along that diameter that connects P and the centre of the circle. And this is very similar, therefore, to a pendulum, because we have this blue mass here, which is confined to this ring, and it's subject to this force that's moving outwards. And so basically, this particle will execute simple harmonic motion around this ring due to that centrifugal force in this co-moving reference frame. Now, if we were to go to the non-moving reference frame, our original x and y coordinates, we'd see something very complicated. As the ring was moving around, the particle would be kind of bobbing backwards and forwards in a very complicated way. But in the co-moving reference frame, we reveal the physics for what it is, which is simple harmonic motion around this axis. So the last example in this lecture will just be a little bit of fun. I'm not going to do this in a lot of detail, but I would like to illustrate the application of classical Lagrangian mechanics to the topic of medieval siege warfare, obviously. This is a nice example of classical mechanics, as we'll see, and the example that I'll be considering here will be that of the so-called trebuchet. The trebuchet is a kind of catapult. We imagine we have some kind of pivot here which supports this red lever, and then to this short end of this lever we add a large mass, capital M. On the other end we attach a rope and a sling with a smaller mass, little m, inside this thing. And this little mass m is going to be the projectile, which we're going to fire as far as we possibly can using this trebuchet. So how do we do that? Well, at t equals 0, we lift up the mass as shown here, and then we let this thing go. Under gravity, this mass here will fall down to Earth, and that will rapidly swing our projectile here around. So this first part of the motion, the projectile will still be inside the slingshot, and the acceleration of this little mass m will be due to the acceleration of the big mass up here falling under gravity. So a few seconds later, the blue particle has fallen down. This has elevated our slingshot right to the top here, and then there's some kind of release mechanism that allows this projectile to be hurtled in a ballistic fashion towards the unfortunate target. So by ballistic, what I mean here is the particle is free and falling just under gravity, subject to the initial velocity, which is something that's determined by the initial part of this motion as drawn. So what happens in this second ballistic part of the motion? Well, clearly this particle is fired a great distance, hopefully, towards the target. And this bit is just regular motion of a particle falling under gravity with some initial velocity. And you can imagine tuning the initial conditions, the mass of the object, and the length of the rope, and the release condition for the projectile from the slingshot and so on, in order to tune the range, as it's called, which is this distance here from the trebuchet to the target. So all of what I've described here is just regular classical mechanics. We have two particles, the blue one and the projectile, which are tied together with the constraint of this lever here, and we have two parts to the motion. There's an initial part, which is described by this dotted line, where the projectile is inside the slingshot, and we can solve that using regular Lagrangian mechanics. And at the end point of that motion, up here, we will know the velocity of the projectile, and then we consider regular ballistic motion, where the particle is just falling under gravity due to those initial conditions, and then we can calculate this range r. So we actually have to separate this out into two separate pieces. So I won't go through all the equations and the maths. It's very similar to the kind of things that we've been doing already in this lecture. What I want to do instead is to show you a simulation of this and see how we can vary the different parameters and tune the range here of our trebuchet. So I guess they were doing this in medieval times, maybe not solving mechanics using the Lagrangian formulation, but they clearly had an intuitive sense for how all of this works. So that's the last thing I want to consider in this lecture. So let's turn now to the computer simulation of this problem. So this is a Mathematica notebook to simulate the trebuchet problem. Actually, most of that code you saw there is just about producing this graphical interface and making it look appealing. The actual equations themselves are not really so hard. And in this setup, we have a pivot, and then we have a lever, and that lever is broken up into two pieces. We have the front beam, which is the bit suspending the large mass which drives the whole thing. That's this black object. And then we have the back beam, at the end of which we have a sling and a projectile. And here I can change the lengths of all of these things. For example, the front beam, I can change the length of that front beam. The back beam, again, I can change the length of that thing. I can also change the length of the sling and so on. And the idea here is that the motion will be split up into two pieces. Initially, as the heavy counterweight falls under gravity, this will swing around the back beam, and then there'll be some release condition for the projectile, which will then be flung along. That second part then is a ballistic motion. The particle is no longer in the sling, it's just falling under gravity. So let's give it a shot. And we see something interesting like this. So this trajectory is made out of the two pieces, and we can investigate how the trajectory changes as we change the parameters of our system. For example, the length of the back beam and the front beam, as I'm changing here. We can see as we make the front beam very, very short, there's not much potential energy to be gained as the particle, as the counterweight falls under gravity, and that therefore is not converted into very much kinetic energy. We don't get much range out of it. However, as we make that the front beam longer, we can get much greater range from the trebuchet. Likewise, I can change the length of the back beam and see how that affects things. One of the most sensitive conditions, actually, is when the projectile is released from the trebuchet, and that can be described in terms of the angle between the sling and the beam. And we see that as we change that angle, we can get very different kind of trajectories. Either the projectile is flung very, very high, and then it comes down to Earth very quickly, or we can get something where we have a longer range. So the advantage of flinging the projectile high is, of course, it has more power when it strikes the Earth, whereas having a long range, the projectile will be moving more slowly when it reaches the target. So these are all interesting considerations, and one can directly simulate this kind of thing once one has the equations of motion. If one can't solve the equations of motion with pen and paper, one can always resort to a numerical simulation like this one.